Welcome to our presentation on emergent neural automaton policies. Today, we address a fundamental question in robot learning. How can high-level logical reasoning naturally emerge from low-level continuous visuomotor trajectories? Scaling robot learning to long-horizon tasks is extremely challenging. Traditional neuro-symbolic methods offer structure, but rely heavily on handcrafted symbols, limiting their scalability. Conversely, end-to-end VLA models are scalable but lack explicit structure, resulting in poor interpretability and sample efficiency. This brings us to our core question. How can the logical structure of System 2 naturally emerge from the perceptual flow of System 1? To achieve this, we propose a label-free bi-level framework. First, we discretize continuous sensory-motor streams into symbolic clusters. Second, instead of using handcrafted rules, we introduce an extended L-star algorithm. It actively queries the dataset to construct a probabilistic Mealy machine, which acts as an interpretable high-level planner. Finally, this discrete state machine provides a coarse action prior, while a low-level residual network handles precise continuous control. This unsupervised approach yields highly interpretable task structures. As shown here, our method successfully extracts semantically meaningful logic. It discovers topological branching for multimodal goals, and crucially, it learns structural loops. These loops allow the robot to autonomously reattempt an action if a failure occurs. Let's see this in real-world actions. In our first real-world task, stack Lego, the robot must perform a high-precision assembly without force feedback. Notice the real-time state machine transitions at the bottom. The model autonomously discovers a decision point for grasping and uses self-loops to repeatedly adjust its alignment. It will keep retrying until the visual signature matches a successful insertion, demonstrating robust autonomous failure recovery. Next is the multi-goal pick-and-place task, a sorting challenge requiring the robot to match colored cans to their corresponding bowls. Here, our method dynamically branches its latent state machine based on the visual input of the grasped object. It seamlessly shares the common picking skill, then diverges into 3 distinct placing pathways, effectively handling complex multimodal distributions. Finally, the hanger task requires unhooking a hanger and transferring it across an obstacle to the opposite side. This demands a strict causal chain of movements. Our method's learned state machine cleanly segments this long horizon trajectory into distinct visual phases, guiding the residual policy to safely execute the complex transfer. Thanks for watching.